Okay, today we'll see what's the work and kinetic energy. That is what's work, what is kinetic energy. We have seen work and kinetic energy are a scalar physical quantity. There is the same, it is the same, which is joule. Also, this Newton times what matter. That is what the same physical quantities. And such works has can be related work and kinetic energy have some expressions or some theorems, which is known as work-energy theorem. The resultant force changes what the values of an object and it does work on the objects. Under this lesson, we have seen that the work energy theorem. There is what's the relation between what work and kinetic energy. There is basically we have seen that the mathematical expression what work. Work is equal to force times what displacement, which is along the direction of what force. And the kinetic energy also defined by what half of mv squared. Any object having what mass m and velocity has possesses kinetic energy. Under this concept, we have seen that the relation between such forces or such phenomena. Therefore, under this one, there is considered what such systems. In this case, we see, as I told before, the resultant force can change what velocity of an object under what work done and does work on that objects. This what such objects can move initially without what force applied F. This object initially moving what velocity of what V naught. After applying what a force, external force or resultant force of F, this object can gain what a final velocity of what V F after what displays what a distance of x. Therefore, under this condition, there is what work done. This work done is equal to force applied times what the displacement x along what the applied forces. The same is true. There is a kinetic energy. There is what since there is change in there is a change in velocity. There is a change in kinetic energy. There is half of mv squared, and this is what we have seen. There is work done. The general form of work done is equal to force applied times what x. But there is force is from Newton's second law. Force is equal to what mass times acceleration. There is also mass have their own calculations or general mathematical expressions. We have given that v final square minus v initial square over 2x. Such expressions can be inserted to this one, and we have given what the work-energy theorems. If you could substitute such expressions instead of what a or acceleration, we have given there is what this one is for fx is equals to 1 over 2 mv square final minus 1 over 2 mv not square. This leads to what the theorem, work-energy theorems. Therefore, work is equal to what change kinetic energy. We can conclude or we can generalize that work if there is what force applied. In this case, we have leads to or this leads to what the theorem of what kinetic energy with work energy theorems. There is changing kinetic energy also work done. There is what if we have defined kinetic energy as what half of mv squared, then we can state a very important physical principle which is known as work energy theorem. And this can be said that the work energy theorem states that the work done by a resultant force is equal to what changing kinetic energy that it produces. This is what the work energy theorem. Let us see some examples that is related to what such expressions. There is what 2 Newton, 200, 20 gram projectile strikes a mud bank, penetrating what distance of what 6 centimeters before what stopping and there is what then find the stopping force F if the interference velocity is that is 80 meters per second. There is, as we have seen from this diagram, there is what this bullet has their own what velocity, which is 80 meters per second, which is moving in this what, and also it penetrates what 6 centimeters. This mud, and there is force applied. Therefore, what will be the force applied to stop such moving objects? These expressions or such constants can be explained or defined or calculated or computed by what work energy theorem. Therefore, as we know that from work energy theorem, there is what work energy equals to half of what mv square final minus half of mv naught square. This is what the initial velocity of what the objects. This expression also equal to what f times what s. This is initial, this final velocity is 0. Since stopping, there's a concept of stopping, the final velocity is 0. Therefore, this expression is 0. Therefore, finally, this work done also equal to what? Force times x, and also equal to minus 1 over 2 in half of what m v naught square. Then that when we substitute what the value of what x and m and v naught, we have given this one. The angle between what the force applied and also force applied is frictional forces. We can take as this restoring forces, can take as frictional forces. The displacement can be in opposite direction. Therefore, the angle between what such displacement and forces is 180 degree. Therefore, cos 180 degree gives what? Minus 1. Therefore, we have seen this 0.06, which is centimeter to meter. There is 0.06 meters. That is cos 180 degrees minus 1 is equal to when we calculate such expressions, we have given what the negative 64. Then finally, force equals to 1067 newtons. This is what the restoring force to resist the moving objects. Resist what? Such moving objects. This is back to this example 2. Example 2. When we come to example 2, a bus slaps what on brakes to avoid what an accident, and the tread makes what of tires are 80 newton. 80 meters long. If the coefficient of kinetic friction is 0 by 0.7, what was the speed of what? Speed before what applying the brake? These expressions of such problems also computed by what using what the work-energy theorems. This the work done is called for the changing kinetic energy. As we have seen this, there is a force. This object can displace 25 meters along such directions. There is called frictional forces. Therefore, what will be the speed of what such objects before what stopping expressions? Okay, work done. There is work-energy theorem. There is work square, so changing kinetic energy. Therefore, from this one, there is an angle theta between what force F cos theta times x, where theta is angle between what such displacement and such forces. Therefore, we have seen that F the frictional force also has mu t times n, that is also mu t times mg. The normal force is under such conditions normal surface. Since the surface is normal, the normal force is equal to mg. Finally, we have given that work done is equal to minus mu k times mg x the displacement. Then the initial velocity of such object, final velocity of such object is 0, since the there's frictional forces. And finally, we have given such expression. Then this is 0, and therefore this come to this one, and this one is this. When we equalize, we can find what the final results of the required basic requirements. Is what. Then finally, we have seen there is two. This is what the velocity of what such objects. This is all about today's lesson. Thank you very much. If it is interesting, let us subscribe and also like it. Thank you.